At negative 459.67 degrees Fahrenheit, motion doesn't vanish, it becomes a whisper. We'll trace the staircase toward that unreachable wall, where light slows atoms like soft molasses. Crowds of particles merge into one calm voice. Helium forgets friction, and wires carry current without loss. Zero isn't a cliff, but a horizon, and in its nearness, matter reveals new songs, quiet, precise, astonishing. Before we drift on, I'd love to hear from you. What's the coldest moment you've ever felt? Was it a biting winter wind, a night where the frost seemed to reach through your coat, or maybe a moment that had nothing to do with weather at all? Just the kind of chill that stays with you. Share it in the comments. I'm curious where and when it found you. Imagine a small room at night, a single lamp, the window a darker square within the dark. On the sill, a cup of tea has been forgotten, still warm, not hot. The sort of warmth that reminds your hands of winter walks and scarves, and a key turning in a quiet door. You can see the steam if you look sideways, not directly. It rises and dissolves, like a memory that knows it isn't needed. Every tendril is a small story of motion, water molecules slipping free, carrying energy away into the room. Heat always does this. It flows from where there is more jostle to where there is less, from the lively to the calmer, until everything agrees on a gentle middle. If we could listen inside the cup, past the porcelain and the tea and the air above it, we'd hear a delicate crowd, molecules bumping and ricocheting, not with the sharpness of billiard balls, but with a quiver more like moth wings against a window pane. The average jostle, how vigorous those tiny motions are, is what we call temperature. It isn't a feeling, but it touches our feelings. It isn't color, but it glows in our minds as red and blue. Temperature is the story of motion made simple enough to hold. Now, if we dimmed that lamp a little more and watched the tea settle, we might wonder what happens at the very bottom of this settling. If we could keep carrying energy away, again and again, cooling and cooling, what would the last degree be like? Would motion end? Would the jostle surrender to a perfect stillness, the kind that feels like snow when the city has paused to listen? Physicists gave that question a special number. They imagined a scale, not anchored to ice or salt or weather, but to nature's own hush. 0 Kelvin, not a place we can walk to, not a winter we can forecast, but a limit toward which motion thins. On our familiar Fahrenheit scale, people note it as 1/4 degrees. The number is sharp, but the place is soft, an edge of possibility in the landscape of warmth. Perhaps you remember learning that heat is energy, and that energy hides in countless forms, in whirling particles, in vibrations, in the subtle disarray of arrangements. At absolute zero, we might expect all those forms to curl inward and rest, like cats folding themselves small. But the story has a shimmer that refuses to vanish. In the smallest theatre, the quantum one, motion is threaded with uncertainty. There is a kind of irreducible quiver, a 0-point hum, that remains even when we speak of the ground state, the lowest possible energy. It is not a violation of stillness, so much as stillness is texture. A silence that isn't mute, but alive. So, the last degree is not a cliff. It is an asymptote, a line we approach by halves and half-agains, the way a sigh approaches quiet after a long day. Each step colder is harder won than the last, as if the universe had made a promise that we may approach the border, but never touch the wall. This promise has a formal name you might meet later, the third law, but tonight we can simply feel its shape. Limits, gently placed, keep worlds from tearing. Outside the window, the air is a little cooler. Perhaps you can imagine the night sliding a few degrees down as the hours pass. Temperature is touching everything. The glass, the page of a book, the blanket, your own hands, and without drama, they're negotiating a truce. The warmth in the tea moves into the air. The window pane whispers it to the outside. Somewhere a radiator clicks and sighs. All of this, a choreography of sharing. If we pulled back, way back past the roof lines and the dark river, past the continent, curving into cloud, we would see that the earth is forever making these trades. Sunlight arrives as a blue stream of order, and the planet re-sings it as a redder, milder warmth. Day yields to night. Summer listens to winter. The deep ocean is a reservoir of patience, storing and returning heat, like the calmest banker of time. And in the farther dark, space itself has a background cool. Not quite the bottom, but an ancient near whisper of warmth, left over from the universe's first light. Even the cosmos is not at zero. There is always, it seems, a last little glow. Back in our room, the steam thins. The cup is now only warm to the palm. If you lifted it, you might feel the way heat prefers a path. The handle cooler than the bowl, the rim cooler than the heart of the tea. In metals, energy slides easily, as if the lattice of atoms were a good conversation. In wool and wood, heat stumbles, pausing at every knot and twist. Conduction, convection, radiation, three ways of sharing, three dialects of the same story. You don't have to name them, you already know them with your skin. Once people thought of cold as a substance that entered things and dimmed them, like blue ink soaking into cloth. Then the story turned around. Cold is not a something, it is a less of something. It is the absence of thermal energy, the quieting of motion. This is not just a philosophical turn, it's a gentle flip of the lantern that lets us see the room more clearly. When we speak of cooling, we speak of removing energy, of giving atoms fewer ways to dance. At the limit, we imagine a dance floor nearly empty, only that 0-point sway remaining, compelled by the rules of the very small. What would that feel like, if feeling were possible down there? In certain materials, as we will visit later, the approach to the last degree rearranges identity, separate ripples merge. Particles that once insisted on their separateness begin to act as one. Friction vanishes in places. Resistance reconsiders its duty. It is as if the cold teaches matter to harmonize, to hum in chorus rather than chatter alone. Many becoming one, an old dream wearing a laboratory's badge. But before we hurry to those marvels, we linger with the cup. The last visible thread of steam, a faint, translucent ribbon that unravels and disappears. You might notice the way the glass of the window has cooled beneath it, leaving a tiny ghost of breath on the pane. That ghost is a map of exchanges. On one side, a room practicing warmth. On the other, the night, generous in its emptiness. Between them, a membrane where countless molecules arrive and depart, and arrive again too small to name, too busy to notice. If we could shrink ourselves and sit among those molecules, if we could become observers with no weight at all, we would watch statistical kindness at work. Not every molecule moves at the same speed. Some are quick, flicking like minnows. Some are slow, heavy with their own daydream. Temperature is the average of all this restless democracy. To cool the tea is to favor departures of the quick ones, to lower the average by letting the nimblest leave first. In a moment we will see how scientists coax this process along with light itself. But for now, the night is doing the work, patient and without equations. There is a temptation, when speaking of absolute zero, to slide toward the stark, toward words like dead, or frozen, or empty. But that isn't what the bottom offers. The closer we come, the more we discover textures rather than voids. Patterns become cleaner, noise thins to reveal delicate signals underneath. We find that matter can be persuaded to braid itself into new states, to circulate without loss, to carry currents without friction. It isn't death, it's a listening. And so, there is comfort in knowing that the last degree is not a cliff to fall from, but a horizon to look toward. On a winter morning, there is a special brightness to the cold. Sound travels crisp and near, our breath becomes visible. We can see our own warmth leaving, and that visibility makes the exchange less abstract. In that same way, absolute zero gives us a way to see the secret life of heat. By imagining its absence, we better understand its presence. If you like, let your hands rest, palms down, feeling the surface beneath. Notice how quickly your skin detects the nature of that surface. Wood's calm, metal's early bite, fabric's soft refusal to take your heat too fast. Your nerves are exquisite thermometers, not in numbers but in comparisons. They tell you the direction of flow. They tell you which way the warmth is traveling. Tonight, the arrow points outward from the tea, outward from your skin to the air, outward from the lamp's little sun to the walls it keeps warm. All those arrows, tiny and unhurried, bending toward a shared balance. There is a kind of slow kindness in balance. Not everything needs to be equal at once. The room drifts toward its overnight temperature. The city gives its day heat back to the sky. The ground, a deep archive, keeps its own counsel. We too are archives of days, of conversations, of sunlit walks. As your body cools by a degree or two for sleep, hormones whisper to muscles to release their hold, to the brain to ease the bright chatter. Cooling, in living things, is often an invitation to rest. We are not separate from the physics we describe. We are its soft expression. And so the last degree, this fabled bottom of warmth, becomes a mood as much as a measurement. It is the mood of settling, of exhale, of patterns becoming simpler and truer than they were at noon. Perhaps it's why winter nights can feel more spacious, why stars seem nearer when the air is cold and dry. Motion hides less in the quiet. The world's smallest music can be heard. Our cup is nearly cool now. If you place a fingertip against the porcelain, it's no longer a refuge from the air. It is part of the room's agreement. Somewhere in the walls, pipes carry water that has forgotten the heat of the afternoon. Somewhere in the sky, a satellite feels sunlight and shade in quick alternation, its metal skin practicing a kind of thermal breathing as it circles the earth. Somewhere in a basement or a lab, a cylinder of helium waits, its own strange coldness a promise. We have not reached zero. We never will. But we have found its presence in the way things lean toward quiet, in the way motion yields to rhythm. We've named its number, not to trap it, but to orient ourselves to a boundary that helps the rest of the map make sense. Let the room hold you. Let the cup be ordinary again. In the next chapter, we'll look at how we taught cold to count, how people, and then instruments, began to place marks along the path from warmth to hush, and why zero, the last degree, had to be discovered with patience rather than declared. For now, listen to the house settle, the softest creaks, like punctuation in a long, calm sentence, and feel how the night gathers around you, not as darkness, but as a quilt of slow, steady motion, thinning, quieting, almost still. Before there were numbers for cold, there were gestures, hands held over a fire, a pot lifted from a stove to just before the boil, a baker's palm hovering inside an oven to judge the readiness of bread. Our ancestors measured with skin and habit, with words like chill and bitter, and biting. It was enough for a long while. Winter arrived without a scale. Tea cooled without a number. Then curiosity began to ask for marks along the way. Imagine a simple glass bulb, slender-necked, half-filled with spirit. When the room warmed, the liquid rose. When the room cooled, it fell. No numbers, just motion, up and down, a tiny tide. Early instruments like this were called thermoscopes, not thermometers, because they showed change, but did not yet agree on how to count it. Still, the idea was planted. Temperature could be traced by something that swelled and settled with the air. In time, people began to anchor these motions to moments everyone could find. Ice that melts at a certain steadiness. Water that boils when its bubbling refuses to grow any louder. Pick two events. Put small marks at their heights. Divide the space between them, and suddenly the world has a new kind of ruler. One winter, in the early 1700s, a craftsman in Danzig, Daniel Gabriel Fahrenheit, polished glass that held a new clarity. Mercury, dense and obedient, replaced the timid spirits. He chose points to trust. A salty brine that seized into ice at a low, repeatable cold. The mixture of plain ice and water at a milder stillness. And the warmth of a healthy human body. 03296. Later, the boiling of water would settle at 212, and body heat would be nudged to 98.6. But the idea was already walking on its own legs. The Fahrenheit scale let people name their winters, their kitchen tasks, their weather. Stories could now say a 20-degree morning, and be heard the same way across towns. Elsewhere, a Swedish astronomer, Anders Celsius, offered a simpler ladder. The distance between freezing water and boiling water divided neatly into 100 steps. He first placed 0 at the boil, and 100 at the freeze. An upside-down world in which heat ran uphill, but his colleagues soon turned it the way our senses prefer. 0 for the hush of ice, 100 for water that cannot be kept from leaving itself. The Celsius scale joined hands with the metric world. It was legible, tidy, and it felt like the seasons themselves had learned to speak in round numbers. These scales were practical and human, tied to bowls and kettles, and the way our breath shows in winter air. But the more closely people listened, the more they heard a deeper music beneath the kitchen sounds. Gases, given room, spread. When warmed, they push harder, their molecules flitting more urgently. When cooled, their pressure eases, their volume shrinks. If one could draw the path that a perfect gas would take as it grew colder and colder, the line would point toward a special place where its volume would seem to vanish. Not merely a colder winter, but the end of the road. This, some suggested, is where the true zero must live. William Thomson, who would become Lord Kelvin, followed that line with care. He saw that temperature could be imagined not as a convenience of water and weather, but as a measure rooted in energy itself. How much useful motion remained to be shared, how much push the tiny parts of matter still carried. He proposed a new scale with zero placed at the limit, where no more thermal energy could be drawn forth. Each step would be the same size as a step in Celsius, but the staircase would begin far below it, at a place the older scales could only hint at. 0 Kelvin, no negative steps, no below, just the idea of a boundary that physics itself seemed to sketch. It is soothing somehow to know that our numbers found the floor by following nature's own handwriting. They did not declare a zero as a flag planted on an arbitrary hill. They watched the way gases yield their vigor, traced the slope of their surrender, and noticed the way the world whispers an end that cannot be crossed. In laboratories, a particular kind of thermometer, one that listens to gases, became the ear for this whisper. Instead of spirits or mercury, it kept a gas at a known pressure, and watched its volume, or held its volume and listened to its pressure. These delicate contraptions, lovingly calibrated, told the same story over and over. As the motion inside them calmed, the line on the page pointed to a place around 273 degrees on the Celsius scale. And so the modern numbers, 0K, 273 Tiros of 59.67 Tiuri, entered the family album of science with a certain inevitability. We might pause here, in the hush of that number, and place it beside our cup, on the windowsill. Each degree between room and night is a small crossing. Each degree has a width we can feel under our skin, but degrees themselves are agreements, not objects. They are the spaces between markers we chose. The choice matters. It shapes how the world talks back to us. Historically, water was our teacher. For a long time, an exact and peculiar moment, the triple point of water served as a kind of tuning fork for thermometers. At a certain pressure, ice, liquid, and vapor can coexist in perfect balance, and that balance has a temperature so repeatable that instruments around the world could be coached to agree with one another. Later, as our confidence grew and our definitions became more elegant, the Kelvin found a new anchor not in water's behavior, but in the very relation between temperature and energy. The Boltzmann constant, a bridge between heat and motion. You need not carry the constant's name to sleep. It is enough to know that our numbers now listen to nature at a deeper register, where energy per degree is the true yardstick. And yet, the human scales remain good companions. When a forecast says it will be 2 degrees above freezing in the early morning, we know how to dress. When someone tells us a family recipe needs a low oven, a particular Fahrenheit feels like an old friend. Scales are like languages. Some are better for poetry, some for contracts, and all of them, if translated with care, can say what we mean. As the centuries passed, our instruments grew more precise, less distractible. A thread of mercury under glass gave way to fine wires whose electrical resistance changes with temperature, to junctions of metals that generate a tiny reliable voltage when warmth shifts across them, to devices that read the glow of an object without touching it at all. Each new ear heard a little deeper, a little quieter. Today, there are thermometers in space, listening to the aftersound of the universe, and others tucked into laboratory chambers where the air has been evacuated to a whisper, measuring cold so deep that time itself seems to tiptoe. But through all those refinements, the scales kept their personalities. Fahrenheit, with its many named weathers and kitchen comforts. Celsius, with its clean decimal stride, Kelvin, with its absolute hush, its insistence that zero is not the middle of anything but a boundary you approach, the way the horizon meets the sea. Perhaps you can feel how comforting boundaries can be. Children sleep better with a door closed just so. We rest more easily when a room is a degree or two cooler than the day. Boundaries keep the world from fraying. The idea of an unreachable zero, a gentle wall at the end of motion, offers a similar ease. It tells us that as we cool matter, we enter a realm where each step is harder than the last. Not because we have chosen to be stubborn, but because nature deepens its quiet in a way that resists hurry. This is why laboratories build staircases into the cold rather than elevators. A bath of melting ice, a wash of salt slush, then liquid nitrogen, liquid helium, devices that trick heat into leaving by ever more careful routes. We will walk those stairs together soon. For now, it is enough to know that the numbers we use are more than labels. They are small promises. If you place your mark here, then this will happen. If you touch this point, then that behavior will appear. The way a scale is built shapes our stories. With Fahrenheit, boiling and freezing are neat whole numbers, but absolute zero is a distant, precise fraction. With Celsius, the watermarks are easy, and zero is also the way our breath describes winter. With Kelvin, zero becomes an ideal you cannot step beyond, and every temperature is a counting up from that ideal, a measure of how much motion remains in the room. Think of a musician tuning to a standard pitch. A is chosen to be 440 cycles per second. The choice is conventional, but once made, it lets orchestras agree. Temperature scales are the same kind of kindness. They let laboratories on separate continents cool an atom cloud, and know they mean the same hush, the same nearly shared ground state. They let doctors check a fever and know, across languages, what the body is saying. And just as music has keys, minor for the wistful, major for the bright, our scales come with atmospheres. Celsius carries the weather, Fahrenheit carries the home, Kelvin carries the cosmos and the machine. When we speak of 144.67 on the Fahrenheit ladder, we feel how far the household world stretches. When we speak of 0K, we feel the elegance of a limit inscribed in the rules of the small. It is tempting to crown one scale as truest, but perhaps it is gentler to see them as windows on the same garden. Each window frames the path differently. Each will show the same bird if you wait, the same breeze through the leaves. The physics does not change. Only our vantage does. As the cup on the sill cools into the room's quiet, your body may be settling into its own preferred number for sleep. Humans are little furnaces, steady and warm, but we like the air around us a touch cooler, as if the skin wants a reason to pass some heat outward, a slow drift that encourages the rest of us to follow. In that drift, our chemistry takes its cues. Hormones move with the temperature's lullaby, muscles loosen, thoughts unbraid, so we mark the cold, and in marking it, we find a rhythm that helps both science and sleep. A baker can promise a crust, a physicist can promise a phase transition, a traveler can promise to wear gloves on the dawn train. Numbers earn their keep not by being perfect, but by being the right kind of simple. Let's stand once more at the window and look past our reflection. The city is quiet, or quieter than it was at dinner. Somewhere a weather station lifts its white louvered face to the night, listening. Somewhere a satellite passes over, its instruments nestled in shields that hold their temperatures steady like a heartbeat. Somewhere a student watches a thin metal coil respond to a snowfall's arrival, the coil's resistance changing by a whisper. The instrument can hear. All these listening tools, all these scales, point toward the same horizon. They do not claim that we can walk to zero. They show us that it exists as a direction of travel, a promise that as motion thins, new textures appear, textures that were hidden by the jostle of noon. In the next chapter, we will draw closer to the wall itself, the third law of thermodynamics, which suggests that the colder you go, the harder each additional step becomes, and that absolute zero, though it shapes our maps, remains beyond our fingertips. We will treat this not as a forbidding rule, but as a kindness, a limit that keeps the mysteries intact and gives us the pleasure of approaching without the burden of conquest. For now, let the numbers blur into comfort. 32, 0, 100, 233. They can nestle beside the sound of the house settling and the faint whisper of your breath. Warmth will go where it must. Cold will receive it. The scales will keep the peace, quietly counting as the night, degree by gentle degree, carries you toward rest. Snow has a way of softening edges. Even the hard geometry of a city yields under it. Curbs blur, footsteps round themselves, corners lose their sharpness. If you've watched a slow snowfall from a window, you know how the world seems to hush by degrees, as if every flake were a reminder, quieter now, and quieter still. The physics of cold, when it goes deep, carries a similar hush, not a silence of nothingness, but a careful reduction of chatter. The third law of thermodynamics is our name for this deep, quiet's boundary. It is an almost poem disguised as a principle. As temperature approaches absolute zero, certain measures of disorder, entropy, approach a minimum, and absolute zero itself cannot be reached by any finite series of steps. It is the idea of an asymptote written into nature, a horizon that recedes as we walk. Entropy is a slippery friend. People often call it disorder, and in some moods that works. But tonight, let's think of it as the count of possibilities. Imagine a tidy room, not museum tidy, just lived in and cared for. On the surface, there is order, books in a line, a cup on a coaster, a sweater folded. But beneath that calm, there are many ways the fibers of the sweater might settle, many slight positions the cup might adopt on its ring. Countless micro-possibilities of air and dust and wood. Entropy is the arithmetic of those possibilities. High entropy means many arrangements are available. Low entropy means only a few are permitted. Temperature, the average jostle changes how many arrangements matter. At high temperatures, the room's fibers, the atoms in the cup, the vibrations in the wood, all have the energy to explore many configurations. At low temperatures, their freedom narrows. The world becomes choosy. Fewer arrangements are allowed to count because there isn't enough motion to visit them. The third law suggests that if we could keep sliding toward absolute zero, the number of available arrangements would dwindle to its smallest. Often just one arrangement, the simplest one, a crystal that has chosen its pattern and keeps it in that perfect quiet. Entropy would rest at a minimum. The room's sweater would be not only folded, but settled into the one fold the universe prefers. But here is the gentle catch. We cannot arrive. We can approach, yes, closer and closer, like the way footsteps in new snow can approach the dark line of a riverbank without ever stepping into the river itself. Each step colder takes more care than the last. Each degree demands a subtler method, a longer patience, a more exact instrument. The wall at zero is not a fence to vault. It is a boundary to respect, a promise that there will always be a last shimmer of motion, a last sliver of possibility. In the language scientists use, one version of the third law whispers that the entropy change associated with cooling a perfect crystal to absolute zero should vanish, leaving that crystal with a tidy, well-defined baseline of order. Another version, the one we feel more directly, says absolute zero cannot be reached in a finite number of operations. The closer you get, the more the world resists your attempt to remove the remaining heat. It is like trying to erase the final stain from a white cloth. Each wash lightens it, but the fabric begins to wear, and the mark becomes the cloth's own memory. Think for a moment about removing heat. At ordinary temperatures, a metal spoon in hot soup becomes a simple bridge. Energy flows briskly along it to the cooler air, but as you cool things, the bridges change character. The spoon becomes a poor messenger. The pathways for energy to leave grow fewer, narrower. Heat capacity, the ability of a thing to hold and exchange thermal energy, tends to dwindle in the cold. You are asking a sleepy world to give up its last drowsy murmurs. It will a little, but slowly, and then more slowly still. One way to feel this is with a story from the lab. Imagine a tiny cloud of atoms trapped by magnetic fields, hovering in a vacuum so empty that dust would seem like a crowd. Lasers have already done their part, washing the atoms with light in a way that steals their motion. The cloud is cold, microkelvin cold, then nanokelvin. At this point, to go colder, researchers often use a method with a lovely, homey name, evaporative cooling. They allow the liveliest atoms, the ones that still carry more than their share of energy, to escape the trap. exactly as the liveliest molecules of your tea steam away into the room. The average energy of the atoms left behind drops. The cloud cools. But the price is steep. You lose atoms. To keep cooling, you must keep letting go. Each fraction of a degree asks for a larger fraction of your company to depart. At some point, there is nearly no one left to cool. Other stairways into the low-temperature world make the same promise and the same refusal. A dilution refrigerator, with its elegant mix of two flavors of liquid helium, lets heat trickle downhill through a quantum landscape. The trickle is slow, then slow. The device can reach astonishing cold millikelvin and lower, but always with labor and time that lengthen as you approach the wall. Adiabatic demagnetization, a method where you line up the tiny magnetic moments inside a material in a strong field, then let that order relax in isolation so that the internal degrees of freedom cool, also thins the last warmth with a patient hand. But the hand tires, the material's messages to itself grow faint. If you prefer a winter image, think of trying to sweep a frozen pond perfectly clean with a soft brush. The first strokes are satisfying. The snow tumbles away. The last dustings are the work of long minutes bent over the ice. The bristles whispering, breath plumbing in the cold. Eventually, what remains is no longer snow, but ice's own texture. You are at the limit of cleaning, because you are touching the surface itself. There are gentle caveats, because nature loves exceptions that are not really exceptions, just reminders to look closely. Some crystals are not perfect even when cooled with exquisite care. Their atoms have multiple nearly equivalent ways to settle. Common ice, for instance, can keep a touch of indecision in the arrangement of the little hydrogens, a residual entropy that persists into the deep cold, unless the ice is guided to a more orderly form. Far from breaking the third law, these lingering choices show its humanity. The law speaks most simply of ideal crystals, structures with a single, unambiguous pattern. In the lived world, small freedoms remain, like the curl at the end of a sleeping cat's tail. Entropy's soft arithmetic also teaches us something about time near the bottom. When possibilities are few, change has less to do. The system's story becomes shorter, simpler. This is not to say that time itself slows. It is more that the cast of the play has been reduced, the dialogues pared down. In such settings, delicate phenomena can be heard that would be drowned out by thermal chatter at noon. Superconductivity, that frictionless current, superfluidity that flow without viscosity, the synchronized hum of Bose-Einstein condensates. These are the arias of the low-temperature opera. They require the hall to be quiet. Notice the compassion in the third law's constraint. If absolute zero were reachable, the world might be too easily frozen into perfect, inescapable arrangements. Information could hide in motionless prisons. By making the boundary a horizon, the law keeps a little motion alive everywhere. A bit of give, a cushion, even the vacuum in quantum thinking, is never sterile. It seethes with the faintest possible tremors. The third law is like a librarian who dims the lamps at closing time, but never extinguishes them entirely. Enough light remains to find the door without stumbling. Now, let's touch lightly the idea behind the law's heat theorem, which is a formal way of saying, as temperature drops towards zero, the amount of entropy you can extract from a system by any reversible process becomes very small, approaching nothing. In friendlier words, the ladder's last rungs are very close together. There is not much room left to climb down. The world runs out of rearrangements to surrender. If you imagine trying to wring a damp cloth dry, you can twist and squeeze and twist again, and at first water streams away. Near the end, your effort yields only a few reluctant drops. Then you are simply holding cloth, and the air is doing the rest. And what of the unattainability? The statement that no finite sequence of operations can bring a system to absolute zero. It has practical faces. Every method of cooling depends on some difference to drive heat from here to there. As the cold side nears zero, that difference fades. Perhaps you can feel a kinship between this pattern and the human experience of perfect calm. You may try to bring a room to complete stillness. The music off, the phone face down, the curtains drawn. There is a silence you can achieve, and then there is the quiet you merely approach. We can even turn the law into a small comfort for the end of busy days. The closer you come to rest, the less work it should take to let the last thoughts go. At first you may need to set aside lists, answer small obligations, straighten a surface or two. Near the end, you are not doing calm. You are discovering that there is not much left to put down. The room of the mind has fewer movable pieces. You are near the baseline of yourself, the simple arrangement that fits the night. In materials, the approach to order at low temperature means the tiny dramas of defects can become visible. A missing atom, a misaligned layer, a trapped impurity. These stand out more clearly when the rest is settled. Scientists learn a great deal in that hush. How a lattice truly holds itself, how an electron prefers to wander, how a magnetic moment chooses allegiance. The third law is thus a teacher as well as a boundary. It invites us to see structure by quieting noise. There is also a kind of ethics to limits. In a world that prizes breakthroughs, it is restful to meet a frontier that asks not for conquest but for respect. The third law has no headline-grabbing rebellion. It is a steady hand on the shoulder, saying, approach, learn, listen, but do not expect to own the last word. In that spirit, laboratories become chapels of patience. Work happens in long arcs. Progress is a series of smaller gentlenesses, not a single dramatic plunge. Outside, the imagined snowfall has thickened. Streetlights wear little hats. The river we didn't cross continues to move under its dark skin, a reminder that motion persists even under quiet. Somewhere, a cryostat hums, a deep, contented note. Inside it, a sample cools toward a record. It will not quite break, will never be able to break, and that is not a failure. That is the shape of the universe consenting to be known without being cornered. If you like, bring your attention to the way the blanket touches your knees, to the small exchange of warmth at that border. Because of the third law's wall, there will always be a trace of motion at that contact, a faintness of travel, heat moving in whispers. The blanket receives your story of the day and returns its own, muffled and kind. In the next moments of our journey, we will follow beams of light as they are used to slow atoms, to thieve away their jostle with a dancer's grace. We will step into rooms where blue-white laser fans make a kind of artificial molasses in which motion thickens and then eases into almost still. But for now, it is enough to feel how a law can be both stern and gentle. You may approach but not arrive, it says, and in that permission, a wide world of near arrivals becomes possible. Condensates, superconductors, clocks tuned to whispers, sensors that can hear the cosmos breathe. Let the snow continue, whether real or imagined. Let the room hold its temperature like a held note. Let the idea of a limit, lovingly placed, be a lullaby. The wall you can't touch is not a denial. It is a promise that there will always be a little motion to cradle you, a last soft hum beneath the floor of quiet. Enough to keep time, enough to keep company, enough to let sleep come. Imagine a room where darkness is shaped, not broken by light. Beams spill in pale fans from the corners, not bright enough to sting, only enough to paint the air a faint blue-white. You can hear what seems like silence. And then, under it, a careful hum, the sound of pumps keeping the chamber inside, nearly empty of air. The tables are heavy to keep the world's tremors out. The mirrors are patient. The wires rest like sleeping vines. It is night outside, or feels like night even at noon, because here the hours are set by lasers, not by the sun. In such rooms, people do something that sounds like a fairy tale. They use light to slow motion. The phrase for it, optical molasses, is playful, but the physics is precise. Light, though weightless to our hands, carries momentum. Each photon is a tiny nudge. If you choose the color of the light just so tuned a touch below the color an atom prefers to swallow, then an atom moving toward the beam will see that light shifted into the sweet spot, will take it in, and in doing so will be pushed back, ever so slightly. The atom re-emits the light in a random direction, a moment later, but the many pushes in the incoming direction don't cancel. Thousands and thousands of these little taps add up. Motion that was fidgety becomes unhurried. A gas that once skittered like minnows begins to drift as slowly as leaves on a still pond. You don't need the mathematics. You can keep the picture a cool, luminous syrup, laid over the air, thickening the atoms' paths. They are not trapped yet, only slowed, as if walking through drifts of soft snow that give and give until your steps become short and careful. The trick that makes the syrup hold its shape is the Doppler effect, the same shift that turns a passing siren's pitch from high to low to atoms. This shift means that light appears a different color depending on which way they move. Set the beams so they come from 6 directions at once, all tuned a half step low, and whichever way an atom tries to wander, it finds a headwind of photons ready to meet it. Motion is met with a little press of light. Over time, the jostle thins. At the center of those beams, another kindness waits. Magnetic fields, graded like a very gentle hill, and circularly polarized light work together to make a soft restoring force. If an atom strays from the center, the way it sees the light changes just enough that it is nudged back. This is called a magneto-optical trap, but that mouthful is simply an embrace, a spring made of color and field, collecting a cloud of atoms as if they were a handful of dim fireflies drifting toward the same quiet. Perhaps you can imagine standing beside that apparatus, in the cool hush of filtered air, watching a display that shows the atom cloud as a small, glowing dot. When the lasers are tuned well, the dot tightens and brightens, then sits there almost proudly, held by nothing you can touch. The atom temperature has fallen from the warm commonness of a room to microkelvin realms, then lower, the last motes of motion reduced to murmurs. In that quiet, the atom's identities, what they are made of, how their inner levels are arranged, become audible to measurement in a way they are not at noon. There is a flaw to this first dance, a limit set by the very Doppler shifts that make it possible. Cool too far with only this method, and the random re-emitted photons blur the last bit of peace you're trying to earn. But nature, mischievous and generous, offers subplots. If you set the light's polarization in a gentle pattern, the atom finds itself walking up and down small hills of energy made purely by the light's structure. It climbs, loses a little speed, and when it reaches the top, its internal state changes so that the hill has moved beneath it, and it must climb again, over and over, like a myth told in a whisper. It is coaxed into giving up motion in a way that feels almost parental. This, nicknamed Sisyphus cooling, can dip below the Doppler floor, though never below the quantum baseline that keeps a last shimmer alive. The stories of Greek hills and laboratory hills find each other miles and centuries apart. Once slowed, atoms become companions. You can hold gently with fields alone. Magnetic traps cradle those with magnetic moments. Optical dipole traps, beams focus to a tender waist, hold neutral atoms by letting them settle into the lowest light-made bowl. To picture it, think of a tiny marble rolling to the bottom of a spoon. The spoon is light itself, bent and bright, and the marble is a single atom drifting toward the softest place. Yet even with all this care, warmth clings. A few atoms in the cloud carry more energy than their neighbors. They dart about, quick and slightly unruly. To go colder, experimenters sometimes do what your tea does. Let the liveliest leave. They lower the walls of the trap a breath, and the hot ones escape first. The average of what remains drops. This is evaporative cooling, not a metaphor, but the same grace by which steam thins above a cup. The cost is population. Each step colder requires another few to be let go, like pruning a tree, until the remaining branches sleep more deeply under less weight. There are other courtesies too. One species can be cooled directly by light and then invited to share its calm with a different species through collisions that favor balance. This is called sympathetic cooling, a kindness in name and in practice. In ion traps, cousins to these neutral atom rooms, individual charged atoms hover above a set of electrodes, stepping to the rhythm of oscillating fields, and are calmed to quantum stillness, one by one, using light and logic. Whether the subject is a single ion or a million neutral atoms, the motive is the same. Make motion simple, then simpler, until the system can be listened to without strain. The timeline of these arts is recent enough to feel like present history, yet settled enough to tell gently. In the late 20th century, people realized that light could do more than reveal. It could guide. The idea that photons, once thought of as only messengers, could become gloved hands was both surprising and inevitable. Awards were given, gratitude shared, and laboratories around the world began to glow with a modest, steady radiance that didn't care what the weather was doing outside. There is a small-scale grandeur to this work. Vacuum is made not by emptiness but by devotion. Pumps whir for days to thin the air, to near nothing, so that atoms will not be jostled by stray collisions. The lasers themselves are quiet clocks, their colors stabilized by feedback loops that listen and correct, keeping each beam as calm as a held breath. Stray magnetic fields are shrouded with layers of metal, the room wrapped in a kind of soft armor so that only the chosen fields can speak, even black-body radiation. The gentle glow of warm objects has to be managed. The equipment shaded so that the world's ambient whisper does not ruffle the cloud. What do we gain by all this patience? At these temperatures, matter becomes more itself, and more together. Spectral lines sharpen. A gas that was a swarm becomes a choir. Measurements of fundamental constants improve in poise. Atomic clocks step out of rough shoes and into slippers, keeping time by transitions, so fine they would be drowned by even a single careless degree. Sensors capable of hearing the minute pull of gravity across a room, or the lightest brush of a magnetic field, or the faintest touch of acceleration, find their voices here. In the cold, the world speaks more clearly, and we remember that listening is a skill as scientific as any equation. There is a humility, too, to the way light must be tuned. If you push at the wrong color, atoms refuse, or heat up, or wander. The beams must be detuned, not to their favorite note, but just below it, like playing the song they want slightly slower so they lean toward it. It is an art of near misses, of almost resonances, of patience with the idea that the right invitation is sometimes the one that leaves room. All of this might sound far from a windowsill and a cup, but the kinship is plain. Cooling is always an exchange. You cannot command stillness. You can only guide energy to a place where it will be more welcome. In a house, that place is the wider room, the glass, the night. In a lab, it is a beam dump, a metal sink, a dilution stage that leads heat away by microscopic staircases. The metaphor holds. We tidy by moving, not by erasing. The third law's wall remains, but with light we approach it more kindly, more deftly, like a skater who learns to stop, not with a scrape but with a slow, perfect glide. If you like, picture a single atom in that trap, a sodium or rubidium or ytterbium, a tiny citizen of the periodic neighborhood. It does not know its history, or ours. It knows only that the hills ahead are a bit higher than the ones behind, that the pushes it feels arrive in a pattern that makes wandering less attractive than staying. Over time, its path narrows, its wave, that quantum blur that is as much its identity as any imagined point, spreads just enough that neighboring atoms begin to overlap in meaning. This is where the story wants to go next, toward the moment when many begin to behave as one. But before we step into that chorus, let's linger with the experience of the room. The screens are dim to save the eyes. The notes on the whiteboard curve like small comets. Someone has left a mug by the oscilloscope, the circle at its bottom dried to a faint ring. A graph crawls in slow time, a flat line with tiny bright teeth that means success. The soft thrum of the air handling is a lullaby. Science at this level is not drama. It is caretaking. It is setting conditions and returning to check, tightening a mount, sweeping a cable, polishing a beam. It is putting the world at ease, so the world will speak. And when the cloud is ready, when the temperature has dropped and the density has risen, when the trap is centered like a held breath, something else becomes possible. You can dial the interaction so the atoms, already calm, take the final step into a shared state, a Bose-Einstein condensate, a matter wave choir, the first time one appears on a screen, even recorded in false color and calculated from absorption images. Many people feel something like awe, and then a tremor of peace. We will go there together in the next chapter, unhurried with metaphors set soft as quilts. For now, return to the image of light as molasses. It is a playful comparison, yes, but it holds truth. We are used to light as a swift messenger, a bright line from source to us. It is perhaps restful to imagine that it can also be thick and kind, coaxing motion downward, cupping small things into pores. When the beams switch off at the end of a run, the room seems darker not only because the lights have gone, but because for a moment, the air remembers being syrup. Let your shoulders settle again. The blanket has its own gravity, a patient invitation. Somewhere in the building or in a building like it, a laser locks to its line. A trap waits in the dark. A lab notebook lies open to a page that says simply, "Cloud held." Temperature lower, try evaporative step at 21 tin maze. The handwriting is careful, the future implied. A chorus is about to begin. But between notes there is always a breath. Breathe with it. The night is kind to slow things. The atoms agree. The light, once a blade, becomes a balm. And in that balm, the path to almost stillness opens, one soft push at a time. There is a moment on a quiet pond when the last wind slips away. Small ripples that had been crossing in casual conversation begin to flatten, and then almost magically, the surface agrees on itself. The reflections sharpen. The pond becomes a single patient mirror. Something like this happens in the coldest rooms on Earth. A cloud of atoms, once a busy parliament of jostles and private paths, is slowed and gathered again, until the ordinary differences between the atoms begin to blur. What had been a crowd becomes a chorus. The many become one, not by losing their individuality in a harsh sense, but by sharing a single, gentle rhythm that gives them a common voice. In the language physicists use, this is a Bose-Einstein condensate, a state of matter predicted in the 1920s and first coaxed into the world near the end of the 20th century. That rarest blend of old idea and new touch. If you are willing, we can set the mood in that lab again. The midnight glow, the careful hum, the screen where a tiny image grows out of numbers. An atom cloud has been cradled in light and magnetism. Its temperature lowered to the kind of cold that makes ordinary words like chilly and frozen feel suddenly childlike. The atoms rubidium, perhaps, or sodium have been thinned of their motion, until their quantum waves, which are usually small and shy, swell to a size that matters. At that point, a quiet threshold is crossed. The waves overlap so thoroughly that the atoms can no longer be told apart by their restless wandering. They agree, instead, to occupy the same lowest note available, a shared ground that binds them into one extended, coherent presence. We need very little mathematics to feel the strangeness. An atom is both a particle and a wave. That double life is the quantum story's familiar refrain. At warm temperatures, the wave part is modest, tucked close to the particle's imagined point. As we cool, the wave spreads. When the average spacing between atoms becomes comparable to the breadth of those waves, the world must choose a different description. The cloud behaves less like a bag of marbles, and more like a single, soft-bodied thing that can slosh and interfere with itself. The way light interferes when it passes through two slits and paints stripes of dark and bright. Not every kind of atom will join such a chorus. Nature sorts her dancers into two families. Bosons, named for Satyendranath Bose, who taught the world how to count light quanta, are generous sharers. They do not mind occupying the same state as one another. Fermions, obedient to Pauli's stern rule, are private, each insisting on a unique arrangement. Electrons are fermions, so are protons and neutrons when considered alone. But atoms made from an even total of those spinning constituents behave as bosons, and these are the ones that will, under the right coaxing, merge their identities into a condensate. If you picture a choir, bosons are the voices that happily sing the same note. Fermions are the voices that will harmonize, but refuse to stand on the same pitch. Both are beautiful. Both are needed. Tonight, we sit in the front row for the unison song. The idea itself arrives as a soft thread in history. In 1924, Bose's careful treatment of light, treating photons as indistinguishable quanta and counting their arrangements with a new gentleness, reached Einstein, who recognized the same counting could be extended to matter waves. He predicted that if a gas of bosonic atoms were cooled and thinned just right, an abrupt settling would occur. A macroscopic fraction of the atoms would gather in the lowest energy state, becoming a single, coherent matter wave. It was a thought experiment for decades, a winter bird drawn on paper. Then came lasers, vacuum craft, traps of light and field, and a patience that made the paper bird breathe. In 1995, in a room full of quiet machinery and alert coffee, a small cloud of rubidium atoms, pushed down into the nanokelvin hush, changed its shape on a screen. A broader, thermal lump gave way to a bright, sharp spike. It was the signature of condensation, the many collapsing into a common ground. Soon after, another lab showed the same magic with sodium, and went on to demonstrate a dream made tangible, an atom laser, a stream of coherent matter extracted from the condensate, the way a ray of light is teased from a laser cavity. Decades later, the repertoire would include not just slow, neutral atoms, but more exotic cousins, quasi-particles in solids, light matter hybrids in thin films, each finding its own way to many becoming one. But the first sight of that spike was enough to alter the rhythm of low-temperature physics. If you could stand beside a screen as that transition unfolds, you'd see the picture of a cloud before and after. Above the critical temperature, the shape is familiar, a rounded hill. The atom speed spread in a comfortable bell-shaped way. Below it, a bright needle rises from the center, narrow where the condensate sits, and around it linger the thermal stragglers, a skirt of ordinary atoms that have not yet found the choir's note. The condensate is not all there is. It is a new majority. Warmth never truly vanishes, but it seeds the stage. The beauty of this state is coherence, an ordered phase where the matter wave has a well-defined phase across the entire cloud. That phrase simply means the oscillation that defines the wave is in step, like 100 metronomes gradually synchronizing until they click as one. Because of this, two separate condensates released to expand and overlap will write stripes in space, interference fringes as if they were beams of light. It is one of those scenes that seems designed to confirm a poet's hunch. When similar things agree, they make patterns that are larger than themselves. The condensate's softness, its unity, gives rise to other quiet wonders. If you spin it gently, it cannot accept ordinary, messy swirls. It forms instead quantized vortices, neat pinwheels with exactly defined circulation, like a constellation of tiny holes around which the matter wave flows. Stir it faster, and the vortices arrange themselves in lattices, a snowflake of motion whose geometry depends on the strength of the trap and the interactions inside. Send a gentle pulse through it, and you may watch soliton self-keeping waves slide without fading, curves that preserve their shape in a world that usually smears such things away. The condensate is, in this sense, both delicate and stubborn. Delicate, because heat, rough handling, or too much probing can shatter the coherence. Stubborn because within its calm, certain structures refuse to be lost. The forces that shape it are themselves subdued. In many of these gases, the atoms interact only weakly, barely touching, almost polite. That is a gift. It allows the condensate to be described by a single, smooth wave function, a field of probability that hums in place of countless individual tracks. Experimenters can even tune the politeness, using magnetic fields to make the interactions a little stronger or weaker, to coax the cloud from one personality to another. Dissolve the trap and the condensate swells into space like a held breath. Released. Keep it and you may sculpt the cloud into rings, sheets, or two-dimensional puddles. When new behaviors appear, each geometry, a different lullaby. We say phase transition, and the words sound abrupt, but in the lab the crossing often feels like dawn. Parameters are edged past their thresholds with the tenderness of someone dimming a nursery light. The cloud is imaged, very softly, because even a small probe can warm it. And when the spike appears, when the distribution sharpened itself as if taking a final step into clarity, there is usually a pause that isn't in any protocol. Someone breathes out, someone writes the time in a notebook. Joy, but in library voices. Is this state new in the universe, or merely rare in human rooms? In the cores of neutron stars, in the cold hearts of certain solids, in the whispered flows of superfluids, similar notions of coherence arise. There too, the many align into a single description, a macroscopic quantum order. Our gas phase condensates are gentle cousins to those extremes, laboratory fables that we can retell in endlessly adjustable ways. We study them because they are beautiful, yes, but also because they are clean stories, simple ingredients, well understood rules, surprising emergent behavior. In their calm, we test the grammar of the quantum world. What does it mean for identity when many act as one? The atoms are still atoms. Their labels haven't been scraped off. Yet the meaningful unit for a while is the whole. In that whole, edges soften. The disturbance launched on one side is felt, with measured speed across the cloud. The phase, the shared timing can be nudged here and read there. We can see ourselves in this, if we want. On a winter evening, a neighborhood may move together without planning. The streets quiet, windows lighting in sequence. The same impulse to boil water or draw a bath passing like a soft front. We remain ourselves, yet context lends us a common rhythm. The condensate is not a metaphor for society, but the kinship glows for a moment as the night deepens. There are kind caveats, as there always are. A condensate is never perfectly pure. There is a thermal fraction, a collar of ordinary atoms that ring the coherent heart. Increase the temperature and the heart shrinks. Disturb the cloud too roughly and it shakes off its unity like a dream at waking. Even within the calm, interactions concede instabilities, excitations, ripples that become more than ripples. The state is not a monument. It is a balance maintained by conditions, and that makes it feel alive. Part of the laboratory art is learning how to touch without stirring, how to ask questions that the system can answer without losing its calm. From this unity come tools that feel almost like instruments invented by sleep. An atom laser, a beam of matter that keeps its phase, can be made to fall under gravity and probe fields with a sensitivity that would be impossible with a thermal spray. Interferometers built from condensates can read the tilt of the Earth's pull across a bench, the faint tug of a mass moved by a hand, the quiver of a magnetic field coaxed into existence by a tiny current. In their whispers, these devices become ears for phenomena that would otherwise hide under noon's noise. The first time two separate condensates were allowed to expand into each other, the stripes that appeared were not drawn by a pen. They were drawn by agreement. The darkness in the pattern was not a lack, it was cancellation. The way two calm voices can meet and make a silence between them that is richer than either voice alone. The brightness was overlap, amplification. The lesson has a homely version we already know. When things are in phase, effort adds. When they are out of phase, effort can cancel. But here the lesson is drawn at temperatures where motion is almost gone, and it arrives with the authority of a picture born of numbers, captured in the breath-holding dark. There is a quieter lesson, too, about thresholds. For a condensate to form, a certain product must exceed a certain value. Density and coldness must dance together so that the waves touch. Press too few atoms into too large a space, and even perfect cold will not suffice. Chill them without offering closeness, and they remain a careful, separate rain. Bring them close without calming their speeds, and they jostle rudely, never agreeing on a note. It is the combination, the easing of motion and the kind gathering that makes the chorus possible. Sleep has its own version of this. Darkness without comfort can be restless. Comfort without darkness can be wakeful. We drift most easily when both the room and the body agree on quiet. On the timeline of discovery, the condensate sits like a lantern between older torches. Before it came superfluid helium frictionless flow discovered in the 1930s. Proof that macroscopic quantum behavior was not a fantasy. After it came a blossoming of controlled many-body worlds, fermionic superfluids made from paired atoms that found a way to behave like bosons. Optical lattices, where condensates were placed on artificial crystals of light and made to enact stories once reserved for electrons in solids. The low-temperature landscape, once a plain, became a garden. And yet, the room where it happens remains ordinary in its kindness. Someone sweeps the floor, someone tapes a cable so no one will trip. A sticky note reminds the morning shift to check the cooling water. In this environment, grandeur is proportional to patience. The most astonishing states, the ones that bend identity and make a choir of a crowd, are raised not by shocks, but by lullabies. The lasers are tuned, the trap is deepened a little, then shallowed a little, evaporation is given time to do its cleansing work. Only then do the ripples merge. If you rest your attention on your breath for a moment, you may notice its own threshold behavior. There is a point at which the day's many voices gather into one rhythm, a point at which you stop monitoring and begin being breathed. The condensate is that point for a gas. A system that once needed to be described by countless velocities, countless positions, releases its need for complexity and lets a simpler global description suffice. The mathematics shrinks not by ignoring details, but because the details have agreed to sing together. This perhaps is why the images are so satisfying, even to those who do not speak the equation's language. The spike in the middle is not merely data, it is relief. Soon in our journey, we will visit the cousins of this unity: superfluids that flow without friction, superconductors that carry current without resistance. They owe their grace to similar agreements, different in mechanism but rhyming in spirit. Bosons, agreeing to share, fermions bending their rule by pairing into effective bosons. The world allowing the many to find a single, low-energy way to be together. The vocabulary will change slightly. The metaphors might take on water and wire, but the feeling will be familiar. The hush of a crowd when the lights dim, the moment before the first chord. For now, we can let the condensate recede into its trap, a soft star in a dark room, its coherence intact. The cup on the sill is cool. The window remembers where breath once clouded it. Outside, a streetlight hums, not unlike a lab's power supply. Inside, your body tilts another degree toward rest, and the many small motions that kept the day bright begin to choose a common, slower rhythm. Many become one, and in that one, there is room. Room for quiet, room for listening, room for sleep. There is a hush particular to basements, where great magnets live. The rooms feel softly overprepared, as if they were expecting winter even in July. Tubes carry cold like rivers, carry snowmelt. Metal gleams where hands rarely touch. Somewhere, a cryostat breathes with a calm, regular note, the sound of warmth being led away, step by careful step. In places like these, two lanterns of the near-zero world glow: superfluids and superconductors, matter that, when sufficiently calmed, chooses to move without losing. We begin with a liquid that behaves as if it remembered how to be a wave. Helium, the mildest of elements, resists becoming solid, even at very low temperatures, unless pressed hard. Cool helium 4 past a particular, delicate point, just a handful of degrees above absolute zero, and something uncanny happens. The liquid's character shifts as if a curtain were drawn. Viscosity, that everyday drag which slows honey and gives water its familiar reluctance, thins to nearly nothing. The liquid slips through channels, so narrow that ordinary fluids would refuse them. It climbs walls in a film so thin you barely know it's there, seeking higher ground against gravity's insistence. If stirred, it will not settle by giving up energy to friction. It prefers to keep its motion to persist. Superfluidity is one of the first great songs we heard from the low-temperature hall. How to picture it in the dark of our room. Imagine a crowded square that suddenly becomes a murmuration of starlings. Before the shift, each person walks with private aim, bumping a little, apologizing, making way. After, the crowd lifts as one and turns without colliding. The beauty is not in speed, but in agreement. In the superfluid, the atoms, bosons, happy sharers by their nature, join a common quantum state, much like the condensates we met a chapter ago. The flow acquires a kind of coherence. Turbulence must reorganize itself into neat, quantized vortices, pinwheels of motion, with circulation set by nature's smallest constants. The liquid cannot accept a sloppy whirl. It insists on tidy, countable swirls, as if a skater were allowed only perfect pirouettes. There are signatures of this state that feel like fables told by laboratory glass. Touch one side of a fine filter, warm it a whisper, and the superfluid will fountain through, drawn toward the warmth in an effect both gentle and startling. Strike the liquid quietly with a thermal cue, and not only pressure waves but second sound, a wave of temperature itself can glide through, heat moving as if it were a breeze. These are not tricks, they are the consequences of a system whose motion has become orderly enough that temperature and flow can separate into distinct, harmonious modes. Helium-3, a rarer sibling, tells a subtler story. Its atoms behave as fermions, each unwilling to share a state with another. And yet, under deeper cold, colder by far, these reluctant dancers find a workaround. They pair off two's company, forming composite bosons that can then participate in a superfluid calm. The pairing is not identical to the one we will soon meet in superconductors. The symmetry of the dance steps, the shapes of the pairs, carry their own exotic flourishes, but the mood is familiar. When the many agree on a shared description, losses fade. Turn now to wires that, when quieted properly, forget how to resist. In ordinary metals, electrons move like commuters through a busy station. They are scattered by imperfections, by vibrations of the lattice, those jostles we call phonons, by each other's electric fuss. A current is the net of their progress, and resistance is the tax paid to all that bumping. Cool the metal, and some of the jostle calms, resistance falls, but at a particular temperature for particular materials, the fall is not smooth. It is a cliff. Cross the threshold and resistance does not merely shrink, it vanishes within the reach of our instruments. A loop of superconducting wire, set flowing, will keep its current for a time so long. We measure it in years and understate it as persistent, as if persistence were a small virtue. Beneath this cliff lies an agreement of a different kind. Electrons, the archetypal fermions, do not share easily, and yet within a quiet lattice, the slow breathing of the atoms, the phonons can mediate a delicate attraction between electrons, enough for them to form loosely bound pairs. Two fermions, third, act as a boson. Bosons, as we've seen, are generous in crowds. An army of such pairs can condense into a quantum state with a single global rhythm. Scattering that would usually sap energy now struggles to gain purchase, to disrupt the pair, to knock it from its step, requires a minimum energy that calm metals at low temperature simply do not offer. The result is a current that moves without paying the usual toll. This story is called, in one careful theory, the BCS picture, after three minds who gave the dance its first clean score. The theory is not a lullaby, but its feeling is many things choosing one soft step. Superconductors reveal their calm, not only by what they allow, but by what they refuse. Bring a magnetic field near, and a superconductor will push it out, expelling the field from its interior in a silken assertion called the Meissner effect. In doing so, it becomes a mirror to magnetism, a place where field lines prefer the edges. In certain materials, those that can accommodate fields without losing their superconducting character, tiny threads of field penetrate, each thread accompanied by a quantized whirl of supercurrent. The threads arrange themselves in lattices, neat as frost patterns on glass. Pin those threads to small defects, and the superconductor can hold the field in place, locking into positions with a calm that feels like confidence. This pinning is not a mere curiosity. It lets magnets levitate in stable poise above chilled ceramics, lets practical machines live in the world without blowing out their candles at the first draft. Not all superconductors are alike, and that variety, rather than being a complication, is a garden. Some give up their resistance only at very low temperatures, demanding liquid helium's careful bathing. Others, discovered later, make their transition at far higher temperatures, still cold to the hand, but warm enough that liquid nitrogen, with its more sociable habits, can serve as the coolant. The higher temperature materials are often complex ceramics, their copper-oxygen planes stacked like pages in a well-read book. Their mechanism hints at dances more intricate than the simple phonon-mediated pairing of the early theory. Yet the melody repeats. Pairing, coherence, a gap in available excitations, a refusal to lose energy to the small, aimless jostle. If you listen for parallels, the room fills with rhymes. Superfluids and superconductors both carry currents that refuse to fade. Mass flow in one, charge flow in the other. Both banish sloppy turbulence, replacing it with quantized, tidy structures. Both draw lines across diagrams that say here, disorder yields, and here coherence begins. And in both, the necessary conditions are the same two invitations we keep hearing about. Cool the system until thermal noise is a whisper, and offer a landscape where agreement is more comfortable than the private life. The uses of these states, while not the heart of our nighttime journey, are a soft reassurance that beauty and utility often walk together. In hospitals, quiet tunnels of superconducting wire inside MRI machines carry currents that never tire, generating steady fields that let us image tissues without a cut. In laboratories, superconducting circuits become qubits, elemental units that hold fragile superpositions the way a steady hand holds water to the lip of a cup. In national grids and cables, the dream of lossless transmission shimmers, still complex in practice, but no longer fantasy. For superfluids, the applications are often instruments rather than engines. Gyroscopes, so sensitive they can listen to the Earth's turning as if it were a cat's purr, detectors that hear the faintest ripples in temperature, or rotation techniques that let us probe the secret lives of surfaces and films. The cold is not a museum. It is a workshop lit by small, steady lamps. Yet, perhaps the deeper solace is not in the devices, but in the way these states teach us about limit and kindness. A superfluid climbs a wall in a film almost weightless, an act that looks like defiance but is merely the system taking the lowest cost path to remain itself. A superconductor repels a field, not out of hostility, but because its order cannot coexist with magnetic wandering inside. In both, the world simplifies. Options that were once available become unfashionable, and in that narrowing, perfection is off. We know this feeling in life. When a room is finally tidy, you stop debating where to put the book. The book finds its place. When a mind is quiet, tasks that once took planning happen with gentleness. There are caveats, friendly ones, because the world likes to keep a few threads loose. Superconductors have limits. Fields strong enough, currents large enough, temperatures warm enough will break the pairs and return the wire to ordinary behavior. Superfluids, too, can be prodded into losing their grace if pushed into turbulent regimes or warmed past their soft threshold. None of this spoils the story. It gives it contour. The absence of friction is not a law handed down at all times. It is a treaty kept under agreed conditions, a community standard maintained by calm. If you picture the internal map of a superconductor, there is a gap, a region of energies that cannot be occupied by casual excitations. The gap is small by everyday reckoning, but enormous in its effect. It is the moat around a sleeping castle. Thermal wanderers cannot cross without help, and so the castle rests. Superfluids were a similar moat in their dispersion of excitations. Low energy fluctuations travel as gentle ripples. Higher energy disturbances, if forced, create neat, countable vortices rather than a chaotic churn. In both, the moat keeps the night uneventful. There is a beautiful stubbornness to persistent currents. Somewhere, even as you listen, loops of wire hum with motion that was set in place long ago, and will be there long after dawn, undiminished. A thread of continuity through time, held not by fuel but by order. This is not a metaphor for sleep, exactly, but it is a comfort. Some things, once set right, do not need our constant attention. They keep them. Consider, too, the image of levitation, the famous trick where a cooled superconductor floats above or below a magnet, locked in a posture that seems contrary to experience. The eye delights, the mind searches for wires, and the answer is gentler. The vortices, those threads where field lines and supercurrent share space, are pinned in the material's grain. Motion would change their number or position, and so motion is resisted. The result looks like magic, but is merely a refusal to alter a tidy ledger, balance found and kept. As you rest into the night, you might like the thought that the universe contains these refuges from waste. They are not common in the wild. They require care, but their existence suggests a theme. Where noise recedes, new forms of efficiency appear, not efficiency as in hurry, but efficiency as in grace. Every bit of motion accounted for, little lost to aimless heat. A dancer turning and turning, feet inaudible, the spin sustained by posture more than by effort. We have walked the corridor from atom clouds to helium's uncanny flow, to wires that carry current like water carries moonlight. Along it, the images have echoed, pinwheels, under starlight, lattices of quiet swirls, films that climb, fields that step aside. The details differ in their mathematics, but the mood is shared, many things agreeing to be one thing for a while, and in that agreement, loss falling away. Soon we will listen to clocks that count the faintest ticks, and to refrigerators that build stairways into the hush one narrow step at a time. For now, let the cryostats hum become indistinguishable from the room's own breathing. Let the notion of flow without friction and current without resistance become a feeling in the body, a sense that at this hour you are permitted to move only as much as is needed and nothing more. The blanket keeps your heat, the night keeps its cool. The exchange between them is a well-kept promise. Somewhere, in a basement or a laboratory or a hospital wing, an unseen magnet, holds its field with quiet pride. Somewhere else, a pool of helium glints in low light. Surface still, waiting. These are the lamps of the cold, and their light is subtle. It does not wake, it reveals, and as that gentle light falls across our imagined room, we remember, when motion slows into harmony, the world becomes simple enough to rest in, and to rest we need only agree with it. There is a kind of night when the house seems to lean in and listen. The radiator settles. The street outside trades engines for footfalls, then footfalls for nothing at all. In that hush, the mind begins to notice rhythms that daytime hides. The slow pulse at your wrist, the small sway of curtains with your breath. Time does not announce itself, it accumulates, a gentle counting of changes. Near the bottom of motion, time takes on a different kindness. We often meet time through moving things. Hands around a dial, the swing of a pendulum, the flicker of a quartz crystal. The reliability comes from steady changes that repeat, changes that we can count. But when motion is calmed, when a system draws close to its resting pattern, we might expect timekeeping to falter. Strangely, the opposite happens. In the quiet, the noise falls away, and the purest rhythms come forward, so clean that they can be trusted for years. Cold does not slow time. It reveals the ticks that were already there. In the smallest theatre, even perfect rest has a shimmer. A bound atom vibrates like a tiny spring, and because of the rules of the quantum world, the lowest energy of that spring is not zero but a soft half step above, a 0-point tremor that cannot be ironed out. Electrons sit in their quietest arrangements, yet their cloudy presence still quivers with possibility. Nuclei hold their posts. Lattices in solids carry faint, collective ripples, even in deep night. The universe, it seems, keeps a pilot light on. That pilot light is enough to set clock. Imagine capturing a handful of atoms and inviting them into calm. With light, we learn to slow them. With fields, we learn to hold them. And in that quiet, their internal transitions, those tiny rearrangements of electrons and spins, become exquisitely regular. An atom, when prompted just so, will absorb and emit light at a frequency that is not a mood or a metaphor, but a property of the atom's very structure. Count those cycles, and you have a clock whose hands are waves. The first widely shared version of this idea, listen to a familiar neighbor, cesium. In a chamber not much bigger than a cupboard, a beam or cloud of cesium atoms is guided through magnetic gates and gentle whispers of microwaves. The atoms prefer one hyperfine state, the way their electron cloud and nucleus align. Then the field coaxes some to flip, but only if the microwave's rhythm is exactly right. Too fast and nothing happens. Too slow and nothing happens. Just right, and the atoms change, and a detector nods. The device adjusts itself to stay at that just right. The second, by international agreement, is defined by counting a fixed number of these gentle flips, not a sundial's shadow, not a pendulum's arc, but a quantum tick, so regular that our calendars and satellites and phones all lean on it without ceremony. As the craft of quiet deepened, another family of clocks arrived, optical clocks that measure not billions but hundreds of trillions of ticks each second. They use atoms like strontium or ytterbium, or single ions held alone in electric cradles, and they keep time by transitions written in colors our eyes would call red or yellow. To count such fast rhythms, people built combs of light spectral rulers with teeth set at smooth intervals, so that the clock's whirring could be compared, tuned, and shared. All of this happens in rooms as calm as libraries, where lasers purr and tables do not shake. The atoms themselves are cooled close to stillness, so they do not blur their own ticks by drifting. Sometimes they are pinned in a standing wave of light, as if each atom had its own soft shelf to rest on while it sings. There is a sweetness to the purpose here. The colder the atoms, the less their motion smears the frequency we are trying to hear. The quieter the environment, the less stray field or jostle or heat can tug the rhythm off its center. In the extreme, clocks like these can notice the difference that a change in height of a few centimeters makes, because gravity, too, touches rhythm. Clocks a little higher up run a touch faster than clocks a little lower, not because the devices are fussy, but because space-time itself asks them to. In this way, time reveals itself not as a single drumbeat, but as a field of local rhythms, each one faithful to the ground beneath it. We might ask, softly, what time means when not much is happening? One answer is practical. Time is what we read from a good clock. Another is philosophical and tender. Time is change, and near the bottom of motion change is sparse. So our counting becomes easier, not harder. A system called to its ground state no longer rummages among countless possibilities. It resides. To keep a tally of its rare, precise transitions is to keep a tally of time. Even the way we define temperature now leans on this idea. The Kelvin is anchored to a constant that ties energy to temperature, a link that says, in effect, each degree is a certain amount of average motion per particle. That amount can be traced and compared not by touching a thermometer to everything, but by listening to frequencies, to the way matter sings when gently perturbed. The world's basic units, time, distance, energy, are being harmonized through rhythms that can be measured in the same kind of calm laboratories where atoms are lulled and asked to speak. When we think of clocks, we often think of gear teeth, or quartz slices, or the tidy swing of a weight. But the clocks that set the standard for all the others are closer to music boxes. A field is tuned, a transition is found. The system is kept cool and quiet so the tune will not wander. Then the counting begins. And there is no hurry, because the song does not change with mood or weather. It is not a human song. It is a property of matter, discovered rather than invented. The chronology of these instruments is brief by the measure of sundials and pendulums. A generation or two ago, microwave clocks made excellent time by the standards of their day. Then the idea of cooling atoms and trapping them deeply enough to ask for finer ticks spread like a calm rumor. Optical clocks emerged, outpacing their elders by orders of magnitude. Now they are so steady that two identical clocks in neighboring rooms might disagree only, after longer than civilizations. And yet they are sensitive enough to tell you if one has been lifted an inch closer to the ceiling. This paradox, slow to drift, quick to notice, is part of their charm. There is a parallel, perhaps, to the body. As it approaches sleep, in wakefulness, many cycles compete: attention, appetite, the pulse of tasks. As we lie down, routines begin to align. Heart rate eases, breaths lengthen. The scattered beats of the day fold into a few governing rhythms. In that alignment, the perception of time can change. Minutes soften. An hour becomes a lake rather than a river. The underlying clocks, the ones in our brain and hormones, continue their quiet work, but the noise of interpretation recedes. We become better listeners to our own steady metronomes. Sometimes scientists use clocks to weigh the world in gentle ways. Shift a clock across a room and, by comparing it to its twin, you can infer tiny differences in gravitational potential. The way the Earth's shape and the rock beneath your feet and the mountain down the road lift or lower the local tempo of time. In the future, such comparisons might map groundwater moving under a meadow, or the slow swelling of a volcano, all by listening to clocks that differ not out of error, but out of genuine, local truth. The quieter the clock, the softer the changes it can hear. We should be honest about limits, because limits are part of the comfort. No matter how carefully cooled, atoms do not forget the world. Black body radiation, ordinary warmth from nearby surfaces, still murmurs. Stray fields find paths. Lasers wander a little. Optics drift by hair widths. The best clocks carry long lists of small corrections, each one a kindness paid to reality. That is another way of saying perfection is approached, not possessed. The third law's wall stands even here, though now it is a wall against total certainty rather than against absolute cold. What remains is enough. More than enough. It is soothing to realize that the ultimate clock might be anywhere we choose to keep it well. A rack mount box in a national lab, a lattice in a basement room, under a campus lawn, a single ion hovering, alone, but content, above electrodes drawn like delicate calligraphy. In each, a little patch of the universe is made calm enough to chant its line without faltering. We take that line and share it, sending pulses along fiber, comparing notes across continents, letting networks of clocks correct one another gently, like friends proofreading a poem. Outside our window, the sky has its own metronomes. The earth turns, the moon tugs, pulsars, collapsed stars with magnetic hearts, sweep their beams across space with remarkable regularity. Long before atoms were cooled and interrogated, navigators steered by these larger beats, but even those grand clocks drift, nudged by tides and quakes and winds of plasma. The atomic ones, modest and small, keep steadier counsel, and then the two are reconciled. Astronomical time and laboratory time shake hands each year. The handshake sometimes adds a leap second, an acknowledgement that the heavens and the atoms do not quite agree, and that our calendars must be hospitable to both. Perhaps the most restful thought of all is that we carry clocks inside us that love the cool. The body's core temperature dips at night by a degree or two, and in that dip, cascades begin. Hormones released, memories sorted, repairs scheduled. The cooling is not the cause of sleep, and yet it helps. It sets the stage, the way dimming the lights signals the end of a rehearsal. Our own rhythms become truer when the world around us is a touch colder than our blood. The blankets and the air negotiate, and in their negotiation, we fold inward with ease. If you like, let your attention rest on something regular, the smallest sound in the room, the pulse you can find at the base of a thumb, the rise of the breath, the pause that follows, the fall, and the soft pause after that. Nothing needs to be forced into a cadence. It is already there, and if stray thoughts arrive, let them pass like clouds over a slow pendulum. The clock does not hurry to catch them. It keeps its time. In a laboratory somewhere, an optical clock spends this same night counting cycles of light with unguessable patience. A scientist will return to it in the morning, check a graph that has barely moved, and smile at the stillness preserved. A cryostat hums on the other side of town, holding a device at a temperature where its jitter is almost gone. Signals that would have been lost at noon become visible. Patterns that were drowned in chatter rise, clear as a bell at dusk. Time, it seems, is easiest to hear when we stop trying to rush it. At the bottom of motion, the rhythms show themselves. The second is not a unit of urgency. It is a simple amount of becoming. The clock does not judge whether the moment is busy or empty. It offers ticks equally to snowfalls and to quiet rooms. We will walk, next from these instruments into the broader world of cold-making machines, stairways built into the hush. But before we step, let the notion of a quiet clock settle beside the window, and the cooled cup, and the gentle wall we couldn't touch. The house keeps its pace, your breath keeps its pace. Somewhere an atom, persuaded to sing, keeps its pace. The night is not timeless. It is time, made soft, counted without strain, a lullaby, in numbers small enough to vanish into sleep. Step to the window for a moment in your mind. The sky is the kind of clear that makes distance feel near, as if the stars had taken a step toward you to check on how you're doing. The glass is cool, the room behind it is warmer by a breath. There is a childhood thought that returns on nights like this. Space must be the coldest thing there is, a cathedral of endless frost. It is close to true, and yet, not. Between every star and every galaxy, there is a glow too gentle for the eye, a leftover warmth from the universe's first light. We call it the cosmic microwave background, and it bathes everything in a faint, even hush around 2.7 kelvins above absolute zero. If you left an object far from any sun and let it drift, shielded from starlight, it would gradually cool by radiating its heat away until its own glow matched that background. It would settle not at zero, but at this ancient after-warmth, a few degrees above the bottom space. It turns out, keeps a night light on. That background warmth is not a blanket with edges. It is everywhere, a soft fog that's been thinning as the universe expands. The numbers are not urgent. 2.7 is small, but to reach lower you need more than emptiness. You need a colder partner to hand your energy to, and the universal partner is never quite perfectly cold. It helps to imagine how things cool when air cannot help. In a vacuum there is no breeze to carry warmth away, no neighborly gas to take your jostle and share it down the line. There is only light, your own infrared glow, leaving you in a steady whisper. Put a warm cup in space, and it would cool by shining. Paint it black, and it shines better. Place it in the shadow of a shield that hides the sun, and it cools faster. But even in the deepest dark, the cup's cooling would slow as it neared that background glow. The last degrees are slow, Not because space is unkind, but because the exchange is subtle. The universe prefers gentle trades, and here is a lovely twist. Parts of space are colder than the background, briefly by their own making. There is a small nebula, with a name that sounds like a joke told kindly, the Boomerang, where gas, streaming from a dying star, expanded so quickly that it chilled below the ambient cosmic glow. Expansion steals heat, the way your breath makes a whistle feel cool on your lips. For a while, the nebula's heart is colder than the universe around it, a dark pocket in the night. It will not last. Starlight, collisions, and the omnipresent microwave bath will lift it again. But it reminds us that cold is not a terrain. It's a process, a way of moving energy until the balances change. Closer to home, cold can be surprisingly local. In the perpetual shade of deep craters near the moon's poles, sunlight cannot reach, and the rock radiates its warmth to the sky for millions of nights. Temperatures there fall to tens of kelvins, astonishing to the skin, though still high compared with the cosmic baseline. On the sunlit rim just meters away, the ground bakes under yellow light. Space is not a single temperature. It is a quilt of exposures and shadows, of surfaces drinking or shedding light depending on how they face the great lamps. In orbit and beyond, engineers play a quiet game with that quilt. They build sunshields the size of houses that unfold like paper fans, letting a telescope hide behind them as if crouched under a parasol. On the night side of such shields, radiators spread their dark fins to the cold of the sky and pour heat away without complaint. Instruments tucked there drift to dozens of kelvins, cold enough for infrared eyes to see faint heat signatures from galaxies and dust and planets still warm with their formation. For deeper hush, machines add gentle coolers, pumps and stages that step temperatures down to single digits of kelvins, then to fractions, and in special cases to hundredths. Space helps, but it does not finish the job. A good night needs a good blanket and a quiet fan. Back on Earth, in rooms that hum like contented animals, we have learned to go colder than space itself. We do it not by wishing away the background, but by building stairways into the hush. The first steps are familiar. A bath of liquid nitrogen around 77 kelvins. Winter-made liquid, easy to pour, then liquid helium at 4.2 kelvins, clear as air, light as a ghost, costly to spill. Pumping away the vapor above that helium lowers its boiling point further, slipping toward 1 Kelvin with a patience like watching frost form. But deeper quiet needs a different cleverness. There is a trick at the border between two flavors of helium, helium-3 and helium-4. Mix them at low temperature, and they behave strangely kind. Heat prefers to live on one side of the border. Give it a path, and it will drift across, carrying energy downhill. A dilution refrigerator uses this preference to build a narrow, steady river of heat from your experiment to a sink, and with it you can reach millikelvins, thousandths of a degree above absolute zero, then hundreds of microkelvins, sometimes less, numbers that no winter can imagine. There is another step, more ascetic, adiabatic demagnetization. Line up tiny magnetic moments inside a material with a strong field while the system is still connected to a cold bath, then isolate it and let the moments relax into disorder. In their relaxation, they absorb energy from the material's other motions, cooling the whole by a careful trade. It is like choreographing a yawn through the spins, so the lattice can fall asleep a little more deeply. With this, and with its more demanding cousin that works on nuclear spins, the temperature can fall to microkelvins and below. At those scales, the zero-point shimmer we've spoken of becomes the major character on the stage. You cannot hush it. You can only learn its lines. For single, trapped atoms, another path opens. We have already walked through light's molasses, through traps and evaporative pruning. There, temperatures can be stated in nanokelvins, billionths of a degree above zero. These are not thermometers dipped into a cup. They are temperatures inferred from how the atoms drift when released, from the thinness of their momentum. At that level, space's 2.7 kelvins begin to look positively balmy. The cosmic night would feels like a summer porch to such atoms. They must be sheltered from the world's ordinary warmth with layers of vacuum and shade and care. It is tempting to ask why we go to such trouble. The answers are both luminous and modest. Cold makes whispers audible. Detectors chilled into the millikelvin realm can sense tiny quanta of light absorbed as heat. One by one, instruments kept just above absolute zero can measure magnetic fields so faint they would be drowned at noon. Superconducting circuits, little loops and junctions, hold their delicate superpositions longer, when the chip is neither jostled by heat nor distracted by stray radiation. The reward for each degree surrendered is clarity, and clarity is a kind of peace. Even the sky's own ears learned this. When we built satellites to listen to the cosmic background closely, to map its faint blotches that hint at the universe's first arrangements, we washed their sensors in layers of cold. Space made the first pass. Engineering did the rest. Some instruments carried tiny refrigerators that used the same helium-3, helium-4 dance in miniature, their pumps purring above the atmosphere. Others used sorption coolers, or dual Thomson stages, little staged sighs that drop temperatures one small step at a time. In each the rhythm was the same: shield, radiate, stage, repeat, until the noise thinned and the afterglow could speak. There's a tenderness to the way all this is done. Surfaces are blackened, not for fashion, but to radiate without vanity. Struts are made of materials that conduct heat poorly, thin legs that carry the instrument but not its warmth. Wires are braided and rebraided, so that what must be connected does not become a highway for heat to return. It is housecraft at the bottom of motion. Good insulation, careful vents, doors not left open longer than needed, translated into metals and cryogens and busy quiet rooms. All of this makes a gentle point. Emptiness is not enough. We think of vacuum as the friend of cold, and in a sense it is. There is no air to rub, no convection to bring warmth from elsewhere. But vacuum also removes one path for heat to leave. What remains is radiation, a slower road. To beat the sky's 2.7 kelvins, you must either shade yourself from that glow, or create a local partner colder than the sky to carry your heat away. Space offers silence. Refrigerators offer sanctuary. If you step back to the scale of planets, the story folds into weather. The Earth lives because it is not in radiative balance with the background alone. Starlight maintains a livelier agreement, sun in, infrared out, and the atmosphere's greenhouse keeps some of that leaving for a while, softening nights, blurring extremes. In pure emptiness, an object's dayside can blister while its nightside freezes. In air, heat can be ferried and shared, making climates more like conversations than like headlines. The lesson is not political here, it is physical. Cold and warm are always arrangements, never absolutes. There is also a tenderness in considering time. The universe was once hotter than any furnace we can picture. As it swelled, it cooled, the background glow stretching, reddening, thinning. At some distant future that glow will be cooler still, and the not quite zero of the cosmos will be closer to the wall than it is tonight. Time itself appears as a kind of refrigerator, rolling the temperature down with expansion's slow hand. We live in a good era for seeing the glow soft enough to look past, bright enough to measure. Perhaps, as you rest, you can let go of the idea of cold as a bully. In our house tonight, cold is a courtesy, the air a little gentler than your skin, so heat can leave without hurry. The blanket a gate that slows that leaving to the pace that lulls. Space offers a similar courtesy at its own scale. Sun shields for telescopes, shadows for craters, long lines of radiators pointed at a sky that always listens. We make the most of it by matching our designs to the way the world prefers to exchange. If you're still with the window, the stars are no longer asking anything. They're simply there, steady in their slow motions, seen through a column of air that is itself cooling by radiation into the night. Glass, wood, water, skin, sky, each in quiet conversation with its neighbors, handing energy along until the balances feel right. In the laboratories that chase lower numbers, the same conversation continues, only with more layers, more patience, more ways to say please and thank you to the heat as it leaves. Space isn't cold enough, not for the states we've been visiting, but it is cold enough to teach us how to listen. It shows us that emptiness is not void. It is a medium for light to carry stories away. It shows us that a limit 2.7 kelvins for the universe at this moment is not a failure, but a floor we can stand on to build our stairs. In the next chapter, We will consider a phrase that seems to contradict everything we've said: negative temperature. A notion that sounds like colder than cold, yet turns out to mean the opposite. An oddity of systems whose internal energy levels are arranged like steps on a hill. We will treat it kindly, and then set it down before it disturbs the night. For now, let the image of a radiator under a starfield rest with you. A dark panel, warm at first, then cooling as it offers its heat to the sky's patient ear. The arrow of warmth travelling outward, the room finding its evening, and you finding yours. There's a hill we have been climbing all night, a gentle rise from warmth toward hush, from jostle toward quiet. At the crest of that hill, a strange sign appears, handwritten, friendly, and a little mischievous. Negative temperature. This way. It sounds like a trick, like a door painted on a wall. How could temperature be less than zero when zero is the bottom of motion? How can there be a below to a floor we've called absolute? The kind answer is that the sign does not point downward at all. It points to a different path across the hill. To feel this, imagine those energy levels inside a simple system as steps on a staircase carved into a hillside. Each step is a place a particle might stand. At ordinary, positive temperatures, most of the crowd rests low on the hill. A smaller number occupy higher steps, fewer and fewer as you climb. Add heat, and some of the crowd climbs upward. Remove heat, and they drift down. Entropy, the count of possible arrangements, grows as you add energy up to a point. The middle steps are rich with possibilities, and the system enjoys spreading itself there. But suppose the staircase has a roof. There is a highest step imaginable, a literal upper bound on energy. Some systems have this: spins in a magnetic field, for instance, where up and down are the only rungs. Atoms in carefully built lattices where kinetic energy cannot wander without limit. If you keep adding energy to such a bounded system, you eventually press more and more of the crowd toward the top step. At first, entropy still grows. There are still many ways to distribute people over many steps. Then a threshold is crossed. With most of the crowd near the top, the number of possible arrangements begins to shrink. Press further, and the crowd becomes organized in a peculiar way. Most everyone is up, fewer down, and there are not many ways for that to be true. In the soft mathematics of thermodynamics, temperature is tied to the slope of entropy with respect to energy. When adding energy increases entropy, the slope is positive, and we say the temperature is positive. When adding energy decreases entropy, because the roof forces everyone into a narrower set of arrangements, the slope turns negative, and so does the temperature. Nothing has become colder. In fact, a system at a negative temperature is hotter than any positive temperature, because if you let it touch a positive temperature system, heat will flow out of the negative one into the positive one every time. The crowd at the roof is eager to spill downward. The word negative here is not a direction on a weather map. It's a sign on a slope. It helps to return to the hillside in more homely terms. At positive temperatures, the crowd tends to gather near the bottom, with a few energetic souls on higher terraces. At infinite positive temperature, the crowd is spread evenly. Every step is equally populated. A kind of perfect confusion. To travel from there into negative temperature, you do not continue past zero in any everyday sense. Instead, the crowd inverts. Suddenly, the upper terraces become more populated than the lower ones, an unnatural distribution that can be created only with care. Add a little energy to this inverted crowd, and there are fewer possible ways to arrange it. The system becomes paradoxically more ordered as it is made hotter. That paradox is the hallmark of negative temperature state. Where can such hills exist, with roofs sturdy enough to matter? Not in your tea, not in the air, not in most of the materials of daily life. They appear in systems whose energy levels are bounded, ensembles of spins in a magnetic field, certain cold gases in optical lattices where motion is delicately limited, small, well-isolated parts of larger materials whose excitations cannot wander away without permission. In those places, experimenters can coax population inversions, crowds on the upper steps, by applying fields, pulses of light, or sudden changes of the landscape that leave the system momentarily reshaped, but not yet re-equilibrated. The laser, that civilized ray we use to erase ink and measure distance and play with cats, depends on such inversion. Inside a gain medium, atoms or molecules with discrete energy levels More members are held in an excited state than in a lower one, at least for a while. When a photon passes by that matches the drop from the excited step to the lower step, it encourages a neighbor to fall and emit an identical photon, a chorus instead of a solo. The population inversion is not usually described as a negative temperature in textbooks for beginners, but in the language of bounded levels and entropy slopes, it rhymes more up than down. A readiness to give energy back, a tendency to cool the moment contact is offered. If this sounds like a trick played with definitions, it may help to touch the constraints more plainly. Negative temperatures do not belong to whole open systems that can exchange energy broadly with their environment. They belong to carefully fenced gardens within systems degrees of freedom that can be isolated, that have upper energy bounds, and that can be prepared into inverted populations. The garden must be tended. If you let it mingle freely with the larger world, its inversion will quickly relax back to ordinary, positive temperature calm, shedding its energy and returning the slope of entropy to its common sign. The universe as a whole keeps its ledgers gentle. There is also a kindness to the way negative temperatures fit with our earlier promise that absolute zero cannot be reached. You do not pass through zero to arrive at negative values. Consider the hillside again. Positive temperatures climb from ordinary cool to hotter and hotter, up to that even spread we called infinite. Then the sign flips, not by stepping through the wall at zero, but by crossing a bridge at the top from evenly spread to invert. Negative temperatures run from negative infinity, the just inverted, barely tipped case, toward less negative values, as the inversion strengthens, and in that sense they live on the far side of hot, not beneath cold. The third law sits undisturbed. The wall at zero remains where it was, an unreachable boundary in the language of motion and ground states. Perhaps you can feel how the metaphors want to slide toward the dramatic, hotter than hot, upside-down populations, negative times cousin. We will resist the urge. The laboratory versions are delicate. Their lifetimes can be brief. The systems must be kept in clean isolation. Signals are read softly before they fade. In ensembles of spins, for instance, people flip many of the little magnets against the preferred field, and then watch as the ensemble relaxes, its energy rushing toward the environment through channels that have to be carefully throttled. In ultra-cold gases, on optical lattices, experimenters invert a landscape with a gentle suddenness that leaves momentary imbalances in place, then read the momentum distributions that betray the inversion. The point is not bravado. It is to show that the vocabulary of temperature can make sense in unusual territories provided we keep the assumptions in view. The hillside image has a second use. It lets us speak softly about why negative temperature systems are restless donors of heat. Imagine two neighboring hills, one ordinary and one inverted. On the ordinary hill, people are mostly low. On the inverted hill, they are crowded high. Open a gate between them and let the crowd mix. The inverted hill quickly empties from the top, because there are many ways for a high-step person to descend and distribute among the lower steps on the other side. Meanwhile, the ordinary hill does not have many people eager to climb. Energy flows from the inverted to the ordinary until both reach a shared, positive temperature compromise. No law is broken. A tilted ledger is simply being balanced. There is a philosophical whisper here about the meaning of hot. For daily life, we do not need more than skin and kitchen scales. Hot is a stove, cold is a stream. But deep down, hot is about which way heat prefers to flow. A negative temperature is thus not colder than zero. It is a register that guarantees a particular direction of giving. The sign tells you about that desire, not about frost. We might ask, gently, whether such abstractions have a place in a script meant to soothe. They do, if we let them become images of balance instead of novelty. Negative temperature teaches caution in language and generosity in maps. The world of low-temperature physics is large enough to include a hillside with a roof and a brief party at the top. The party does not insult the valley. It enlivens the description of how crowds move when the hill is fenced. And there is a human echo. Sometimes we, too, find ourselves inverted, full of a kind of energy that wants to flow outward. Thoughts crowded at the top of the steps. The way back to calm is not to imagine a plunge through a wall into perfect stillness. It is to open a small gate somewhere, to let the energy find an ordinary partner to share with a book, a walk, the sky through a window, until the distribution evens and we can rest. Heat, even in us, prefers a path to avoid. If you like, return to the images we've been keeping close. The cup on the sill now cool. The window remembering where breath once wrote a ghost on the glass. The laboratory room with its patient beams and careful notes. In these places, below zero is not a destination. It is a careful phrase, a way to talk about systems where the ledger runs backward for a while. Not because the world has broken, but because it allows a special kind of arrangement under a roof. The quiet truth remains. Absolute zero is a horizon, not a door. The motions that remain near it are textures, not noise. In the final chapter, we will gather what the approach to that horizon reveals, what stillness lets us hear, and how the lamps of the cold illuminate ordinary rooms. We will leave paradoxes folded and put away. We will visit the uses that pay us back in health and clarity, and the meanings that pay us back in calm. For now, let the hillside relax in your mind. The crowd at the top has begun to drift down, laughter low, footsteps soft, the steps themselves cooling under the night. There is no rush. The slope will find its balance, and so will you. There is a point in the evening when the house becomes a companion, rather than a place. The walls feel closer, but kinder. The hall keeps its own mild weather. The books along a shelf seem to breathe together. You can hear the smallest sounds, the tick that is not a tick, but the soft dilation of wood, the distant elevator's sigh, the barely there hush of air meeting fabric. The day has stepped back. What remains is space enough for quiet to show what it knows. We have been walking toward this for hours, from the curl of steam above a mug to the cool logic of zero, from beams of light that slow atoms to the moment many become one, from frictionless flows and tireless currents to clocks that count the tiniest rhythms, from the skies not quite cold to the neat trick of negative temperature under a bounded roof. Each step has been a thinning of noise, a softening of jostle, a settling of possibility into patience. Now we are near the place where the approach itself becomes the message. What does silence reveal? First, it reveals pattern. Noise, useful in its own way, smears details, fills crevices, blurs fine edges. In the cold, patterns come forward, not as decorations, but as the shapes things prefer when left undisturbed. Electrons pair, not out of romance, but because the path of least resistance is literally that, a path with no resistance. Liquids stop grudging and flow like agreement. An atom's inner timing, usually muffled by its own wandering, becomes a pitch we can tune to. The world, offered quiet, chooses coherence. Then it reveals proportion. At room temperature, many effects jostle for attention, their amplitudes stacked like books in a hurry. Lower the temperature, and the stack reorders. Big, slouching influences shrink. Delicate ones stand up. In that rearrangement, truths that were always present take the lead. A single spin's decision becomes audible. A small impurity announces itself. A surface shows its unpolished grain. We discover that subtlety is not the opposite of strength. It is strength politely expressed. Silence reveals memory. Not ours, though, ours answers. Materials hold histories. How a crystal cooled, which direction a field once leaned, whether a stray atom nested where it wasn't planned. At high temperature, those histories are erased and rewritten constantly. In the cold, they linger. The lattice keeps its tail. The vortex remembers where it first circled. The loop of current, once set, persists with a stubbornness that is less defiance than devotion. Even the vacuum, when listened to with enough care, mutters its permanent murmur, the zero-point shiver that will not be stilled. Memory lets us measure. It also lets us forgive. Some traces cannot be fully removed, and the world works beautifully anyway. Silence reveals scale. We are used to thinking that the very small is unknowable without violence, the very large unreachable without glare. But the cold makes both sizes gentler. In a quiet chip, a quantum state can span a device you might balance on a fingertip. In a quiet telescope shaded from the sun, a distant galaxy's warmth finds our sensor without being crowded out by nearer, louder heat. The cold, in this sense, is a bridge, not across distance but across difference. It teaches large systems to behave so cleanly that the small can be inferred, and small systems to hold still long enough that the large can be felt. Silence reveals use. which is a tender way of saying service. We have met some of these uses already. Magnets that peer into the body without harm, circuits that hold fragile superpositions, sensors that read a field no whisper should carry, clocks that notice a change in height no ruler could see in hospitals at night. Patients sleep while currents loop in liquid-cooled coils, fields steady as a hand. In observatories under snow, instruments wrapped like winter birds open their cold eyes to warm light from far away. In basements and backrooms, refrigerators the size of wardrobes, the size of thimbles, the size of matchboxes draw little staircases into the hush, so that a single junction, a pair of atoms, a grain of spin can do its job unhindered. None of this is spectacle. All of it is care, and silence reveals meaning, though only if we approach it without hurry. It reminds us that limits are not insults. The third law's wall is not a closed door, it is a frame that keeps the picture from slipping. The impossibility of reaching zero is not a failure, it is a promise that the universe will always leave a little motion in the world, a last glow to navigate by, a last pulse to keep time, a last give to carry stories forward. We can build wonderfully within that promise. Perhaps you can feel how these revelations have domestic echoes. A tidy table makes a letter easier to write, not because the thoughts are better, but because the clutter has been folded away. A cool bedroom makes sleep more likely, not because the day was unworthy, but because the body prefers a small gradient to guide warmth outward. A boundary on our time, this is enough for today, does not squeeze life, it gives it contour. The physics of almost zero becomes a household grammar, a way of arranging the room so that what matters is invited forward and what nags is gently led out. There is an old question that wakes up around midnight and then, if we're lucky, nods off again. Are we quieter because we listen, or do we listen because we are quiet? The cold suggests an answer that is laboratories that listen best are built to be quiet, and their quietness teaches them what to listen for. We can borrow that. We can build small quiets around the things we hope to hear, whether they are the breathing of a child 2 rooms away, the memory we have been trying to place all week, or the sense that a decision wants to be made and will show its shape if we stop explaining it to ourselves. When people speak of quantum computing, of sensors that can weigh the passage of a cloud, of communications that protect their own secrecy by the very physics they ride on, the words can feel cold in the other sense, abstract, remote. In truth, these machines are warm with human habit. They make lists, they keep schedules, they prefer consistency, they reward patience, they ask us to learn the difference between noise and complexity, one to be reduced, the other to be understood. The lamps of the cold cast light, not just on the future's devices, but on the future's days. We might also admit, with a smile, that silence reveals our limits as observers. The more finely we measure, the more we learn to count our own footsteps. Lasers drift, mirrors creep, cables act like little highways for heat. Even a thoughtless hand on a table can add a tremor to a number recorded as if no one were there. The cold gives precision, and precision gives humility. We are in the data. We are part of the world we study. This is less a problem than a posture. It invites us to inhabit our work the way a person inhabits a chair that fits, aware of our weight, but at ease. In the grandest frame, silence reveals time's direction not as a law carved on stone, but as a habit the universe acquired and keeps. Energy spreads, patterns that require agitation dissolve, unless tended. Islands of order persist where exchanges are controlled. Cooling is a way to control exchanges, to create small islands where the ordinary flow is slowed enough to see against the current. The islands are not separate from the sea. They are its calmer coves, where children learn to swim, and elders like to sit with their feet in the water and remember. We have, in this long night, circled a single idea from many sides, that heat is motion, and cold is its quieting, that zero is a horizon rather than a cliff, that as motion thins, identity changes shape, and with that new shape come new talents. Coherence, persistence, clarity. We have let images stand in for equations. A hill with a roof, molasses made of light, a pond agreeing on its own smoothness, pinwheels under starlight, a radiator talking to the night sky, a clock whose hands are waves. Perhaps those images will linger and make companions of their truths. They are simple enough to carry, humble enough to keep. Outside our imagined window, the sky is the same, and not the same. The cosmic background has cooled a fraction of a fraction while we talked, not enough to notice, but enough to be true. In some small lab, a trap is still holding a cloud. In another, a loop is still humming with currents set long ago. In another, a clock has counted cycles. We will never see, and will never need to question. Somewhere, even closer, a room like yours is easing toward its lowest overnight degree. The radiator is done speaking. The blanket makes a little tent of weather just for you, if you like. Return once more to the cup on the sill. It is cool now. Almost the room. The ghost of your earlier breath is gone from the glass. What remains is a simple thing without drama. Ceramic. Air. A square of night. In this simplicity, the story of absolute zero finds its place. It is not a trophy to win, not a danger to fear, not even a destination. It is a compass point, used not to arrive, but to orient. It points toward the kind of listening that lets the small be heard, toward the kind of patience that makes the strange become gentle, toward the kind of limit that gives shape to everything else. What silence reveals is not silence alone. It is the way we behave in its presence, the way matter chooses harmony when agitation is removed, the way instruments find fidelity when drift is managed, the way bodies find sleep when the room agrees to be a degree or two kinder than noon. We are not separate from these behaviors. We are their soft expression. So let the night keep you. Let the wall you cannot touch be a comfort rather than a dare. Let the last shimmer of motion under everything be a lullaby, rather than a reminder of unfinished tasks. The universe will go on exchanging, one quiet tick for another, long after this chapter is done. It does not need us to hurry. It asks only that we join the rhythm we have been describing all along. If you're still awake, feel free to tell me where you are listening from tonight. A city as it dims, a lake house where the dock creaks softly, a dorm room with notes on the wall, a cabin where the stove clicks and settles. Or say nothing and let the room answer for you. Either way, we have reached the horizon with all the care it deserves. The last degree is not a place, it is a way of seeing. And now, with the lamps of the cold casting their subtler light, you may close your eyes and let the world keep time without you. Patterns held, proportions kept, memories tucked in, scales bridged, uses humming.